Hello and welcome to this video on the RLC circuit analysis. Today we will take an RLC circuit and make two simulations in AC. The first one will be with the directive point AC to observe the impedance between two frequencies. The second one will be with the directive point tran to observe the impedance at a frequency of 10 Hz. Here is the RLC circuit in series we will study. So on the right you have the values of the resistor, the inductor and the capacitor. Then here you have some numbers, so these numbers are the names of the branch. And here I've written the impedance of the circuit and the amplitude of the current ISO of the circuit. Now just below we have something called the resonance, so that's something we will then observe in the first simulation. So to understand this notion, let's have a look at this diagram. So here we have the reactance omega L minus 1 out of omega C as a function of omega. And we can see that when omega is smaller than omega 0, the reactance is negative, so capacitive. And when omega is greater than omega 0, the reactance is positive, so inductive. But what happens when omega is equal to omega 0? So this is the resonance. Let's take omega equal to omega 0, and I define this omega 0 as 1 out of square root of LC. So here we can see that the reactance of the impedance is equal to 0. And here I call F0 the resonance frequency, so omega 0 out of 2 pi. And in our case, this is equal to 1600 Hz. So in this case, the impedance of the circuit is resistive because this impedance is equal to R. So this is purely real. Then the amplitude of the current here, as this term here is 0, the amplitude is now equal to this and is maximal. Okay, now we will observe these notions by means of this circuit. Let's start with the first simulation with the directive point AC. Firstly, we have to configure the voltage source, so right-click, and here we will use the small signal parameters, so the AC amplitude 1 volt. Okay. Now we have to configure the space directive, so spice directive. Help me edit analysis command and select AC analysis. Here we do a sweep of frequency between two limits. The nature of sweep may be decade, octave, linear or list, and here select decade. Then 100 number of points per decade, a start frequency of 1 Hz, and a sub frequency of 100 kHz. Now run, and here on the x-axis we have the frequency. Right click. Here the scale is logarithmic. To observe the impedance, right-click, select Add Traces, and enter this expression V1 out of the current. So this is the impedance of the RLC circuit. Right-click on the left axis and change decibel to linear. The left axis matches with the solid line, and this is the magnitude of the expression, so of the impedance. The right axis matches with the dashed line and is the phase of the impedance. Now attach a cursor and attach it to the phase, and now we can see that at 1.6 kilohertz the phase is 0, and that's what we've calculated before. And now if we go on the right of this resonance frequency, the phase is positive, so we have an inductive behavior. And if we go on the left, the phase is negative, and we have a capacitive behavior. Just if you right click on the right axis, you can choose don't plot the phase. Now right click on the left axis and change the representation from baud to Cartesian representation. So we still have the frequency here, but now on the left axis we have the real part of this expression, and the right axis is the imaginary part of the expression. And this dashed line is the line here of the reactance that we studied before. Now right click on the left axis and choose Nyquist representation. Here we have the complex plane of the expression. On the x-axis the real part of the impedance, and on the y-axis the imaginary part of the impedance. Here we have some irregularities. So why? Because if you right click on the x-axis, you can see that the tick is very, very small. So we can try to do this. Okay, now we have something better here, or maybe just the tick. Okay, now it's better. The real part of the impedance is constant because the resistance is constant, and the imaginary part varies. Now right click on the expression and we will study the inverse of the impedance. So now we will see the admittance. And this admittance is a kind of circle. So why? Because the admittance is the inverse of the impedance. And in the complex plane, the inverse of a line is a circle. So it's a mathematical property. So close. I run again. And we will study the current I attach a cursor on the magnitude of the current, and we can easily notice that we have a maximum of current at the resonance frequency. So let's study the circuit at a frequency of 10 Hz with the directive point tran. First, configure the voltage source with sine, with an amplitude of 1 volt and a frequency of 10 Hz. Then configure the spice directive with the pointron and the stop time of 0.5 seconds. And now run. Now we will observe V1 and the current. As you can see here, we have something a little bit bizarre. So that's the transient state of this system, and we won't study it. So right click and select the left limit of 100 milliseconds. We can observe that the current is ahead of the voltage. So that's because here, if we use this formula, we can then write this, and as the argument of the impedance at the frequency of 10 Hz is negative, we have the argument of the current is greater than the argument of the voltage. And yeah, I can show you with this. Here we have in black this cosine, and in red this cosine with a phase, a positive phase. So a positive phase involves that this second signal is ahead of the first one. And that's why we have this. If we had chosen a frequency for which the phase had have been positive, we had have an opposite effect. Before finishing, I just want to add something concerning your exercise. So sometimes we may give you only the amplitude of the voltage applied on the circuit, but not the phase. So in this case, you have the choice of the phase. And the result then will follow this choice. And I just want to show you this idea. So here I will select a phase of 90 degrees. And run. I change the limit as before. And I display V1 and the current. Okay, here we have the situation with a phase of 0. So the results have the same shape, but just a different phase. That's the only thing. So just be consistent with your choice, and then the results will be correct just with a different phase.